in a ray marched world. Um, Traditionally, objects like actually exist in the world, and then the triangles of those objects are converted into something called clip space, which is just like the space on the screen, and then those triangles are rasterized into pixels, and then that's how the image is made. But this isn't the case for ray marching. Instead, we model objects with something called a signed distance function. This means that we take a point in space and then we return the distance of that point to any arbitrary volume, like a sphere. To demonstrate, we could take this point on the graph and then we calculate its distance from the origin using the Pythagorean theorem. And then we subtract any number we want. In this case, it's 2. And we get the distance of that point from this volume. In this case, the point is inside of the circle. This gives us a signed distance function for a sphere. It's called a signed distance function because it returns a negative number if that point is inside the volume. It also returns 0 if you're on the surface of the sphere. It's kind of cool, I think. But you may be asking yourself, where do the points for the signed distance function come from? And that's where ray marching comes in. Ray marching is formally known as volume ray casting, and it computes 2D images from those signed distance functions. Let's start by looking at a single ray. This is the first point. The first step in the ray marching algorithm is to compare that point with the SDF, or the signed distance function. In this case, it's not. So we're going to move the point forward, or march it forward. And then we're going to check if it's inside that volume again. It's not. So we're going to move it forward, check again, but it's not in. So we're going to move it forward. And then we're going to check again. And then we're going to move it forward. And we check again. And it intersected with the volume. And that's the general algorithm, is you just march these points forward, comparing it with the SDF each time. The result is either it inevitably intersects with this volume, or it goes so far off into the distance that we know for sure that it doesn't intersect at all. But now, again, you may be asking yourself, how do you get images from this? And well, if you imagine the pixels of an image as the beginning of a ray, you calculate that ray marching algorithm, and if it intersects with the volume, then you color it, otherwise you don't. And now we can look at this graph. If each one of these cells is the pixel of an image, we run the algorithm and we get this sphere with that circle SDF we calculated earlier. Now I put together a little Unity demonstration. Here we have this cube here. If you think of the cube as the boundings for one of the SDFs, if I apply the ray marching material here, then we get the sphere using that same SDF in the presentation. The rays are being calculated from the direction of the camera. And this one's kind of boring since it's just a sphere. So SDFs can get like a little bit more complicated. So if I run this, then here's this other SDF I made, which is just some trig functions. It's very fractal. You'll see a lot of ray marched like fractal stuff. That's what Adrian in the Discord does. He makes videos on fractals that are ray marched. And this goes on forever and ever and ever and ever and ever. And it looks very cool. You can also animate it with time and stuff, but I didn't do that because I thought it looked worse. Back to the presentation though. For applications of ray marching, unfortunately, there's not a whole lot of applications in real-time rendering, because if you think about it, calculating the ray marching algorithm for every pixel of the screen, every frame, is kind of costly. So usually ray marching doesn't happen at all for video games, except for parallax mapping, which is a very common technique for stuff like bricks on a wall, because the ray marching algorithm would be less costly than the geometry it would take for a brick wall. And that's demonstrated here. It uses this texture and it imagines it as a volume, and then you ray march it and it creates this illusion of geometry, but it's actually still completely flat. It's very cool, I think. Another very common application is fog. If you ever see something in your video game graphics settings that is like volumetric fog or volumetric lighting, that stuff is ray marched, and it's ray marched from the perspective of the light source. And that's how these light rays are being rendered. It's pretty cool, I think. Anyways, that's about it. Ray marching is kind of simple, but there's so much you can do with it, so it's kind of hard. The real meat of it is in those signed distance functions. Any questions?
I'll ask one, Garrett. So have you done anything in any of your video game graphic design with ray marching, or like you said, it's just not applicable most of the time?
I haven't yet, no. I've learned the algorithm, but everybody makes videos on ray marching, so I kind of just haven't covered the topic yet. I will inevitably though, because I want to make a video on Final Fantasy XIV's terrain and how it's rendered with ray marching.
Gotcha. And looks like you have a question in the chat as well.
Oh shit. Where's the chat? Ray tracing is like ray marching's little brother. Yeah, global illumination uses ray marching. The difference between ray marching and ray tracing is that ray tracing uses a lot of linear algebra to calculate intersections between objects that actually exist. Ray marching uses the signed distance functions, whereas ray tracing uses actual geometry. Yeah, no problem.
Awesome. Anyone else have any questions, comments?
And I'll post the code for the stuff in the Discord as well.
Oh, beautiful. That would be sweet. Yeah, I always keep I'll stop the recording real quick, but